it is about Bell monogamy relations violation. So now we can go to the next slide. Yeah. So okay. So okay. From what I understand, some of the people in audience may not have enough exposure to this area of quantum information. So I have some slides which are somewhat elementary. So I hope some people who know all that stuff will bear with me. So this talk is organized around these headlines. First, I will have just one slide on introduction. Then I will say a few things about two-qubit states. And since Bell violation is one of the key point in this talk, so I will introduce Bell CHS inequality, which a lot of you may know already about. Then we will talk about Bell CHS. So when I say Bell CHS, it usually our usual CHSH inequality. Okay. And then I will talk about Bell monogamy beyond, Bell CHS inequality. Then I will have some conclusions. We can go to the next slide. Yeah. Okay. So I mean, in quantum information in general, in quantum technology also, multipartite entangled states play a major role. And I mean, whenever you look at quantum network, there always you have many nodes, and the state that will be shared will be a multipartite entangled state. So understand, and also these multipartite entangled states, they I mean appear everywhere as soon as we have more than two parties. So understanding the nature of this entanglement is quite important. However, there is a limit to the sharing of the entanglement between different parties. The entangled monogamy relations, they quantify this property. So multipartite entangled states, especially pure states, also exhibit the phenomena of Bell non-locality. So, so there are monogamy relations, for this Bell CHS non-locality. Okay, so I mean, this for pure state at least, entanglement leads to this Bell non-locality. So you should expect, just like you have entanglement monogamy relations, you will have Bell monogamy relations. So what we show that if you have some local operations on some of those subsystems, then you can violate Bell CHS inequality. So in particular, we consider some multipartite W states and show the violation of Bell CHS monogamy relation. We also consider monogamy for beyond CHS inequality, which are multipartite Bell inequality. So Bell CHSH is usually for two parties, but since we are considering multipartite states, so one can go beyond that and look at multipartite Bell inequality. Okay, so this work was done in collaboration with Abhishek Panda from IIT Mumbai and Chandan Datta, who is now at IISER Kolkata. So we can change the slide. Can go to next slide. Okay. Okay, so let me start with the two qubit states. So okay, so if you have an arbitrary two qubit pure states, you can always do Schmidt decomposition and and write in the form which I have written down here. So if you have a two qubit pure state, then which you will start with say 8 real parameters because there are 4 basis states. You have 4 complex coefficients, so you will have 8 real parameters. After normalization, you will have 6 parameters. To start with 8. Now once you do decomposition, which basically involves making local unity transformations, you can eliminate 6 of those parameters and you will be left with only 2. And after normalization, you see there is only one pair. So here this IA and IB, these are sets of orthonormal basis vector for the subsystem A and B. So you have a system AB which has subsystem A and B. And these lambda here, these are non-negative real numbers. They are known as Schmidt coefficients, which satisfy this normalization condition. Actually, this is true for beyond 2 qubit. It is true for any bipartite heuristic. Now, most famous 2 qubit states are known as these Bell states. So you have psi plus minus, which is 0, 1, plus minus 1, 0, and 5 plus minus, which is 0, 0, plus minus 1. These states are actually most widely used in wide varieties of QIP tasks because they are in some sense maximally entangled. In what sense, that we will see in a while. So can we go to the next slide? Yeah. So actually, so whenever you have say, I mean, multipartite state or say bipartite state, there is a possibility of entanglement. If you cannot write the state as a mixture of product state, then it will be entangled state. So there are many measures to characterize the entanglement. For pure states, it is relatively there are many measures. For mixed state, things are a bit complicated. So since we will be speaking about one specific measure called concurrence, so let me just introduce that to those of you who may not be knowing this. So suppose you have a state psi. Okay, so we are talking about 2-qubit, pure state here. Then one can define concurrence of that state as just you take the scalar product of psi and psi tilde and just take the absolute value. So here this psi tilde is basically a state where whatever state you start with say psi, yes, so you go to the what we call computation basis. You take complex conjugate and then you apply this sigma y. Sigma 2 is basically sigma y, and so you apply this operator to psi star. Okay, then you get a state called psi tilde. Then you take the scalar product with your original state, take absolute value. That will give you the value or how much the state is entangled. It will quantify the entanglement. So if you take a product state, then you will find this concurrence is 0. And if you take Bell state, you will find it is 1. So in that sense, Bell state and this concurrence can vary only between 0 and 1. So you see in what sense these Bell states are maximally entangled. So this measure is often very useful because you can easily compute it. You are given a state size, just go to computational basis, take the complex conjugate, and then just apply to cross sigma 2, and just take the scalar product and then absolute value. So it is very easy to compute. So if I go to this Schmidt decomposition, which I had on the earlier slide, their state was like lambda 0. Okay, so if you go to 2-qubit, it will be like lambda 0, 0, 0 plus lambda 1, 1, 1. Because there are only 2 Schmidt coefficients. So one can compute, for that state, this concurrence, and that will be 2 lambda 0 lambda. So what you see from here, if any of the Schmidt coefficient is 0, then it will be concurrence is 0, which is understandable because there is just one term which you can write as a product state. And if you have a Bell state, then lambda 0 and lambda 1 are 1 over root 2 each. So you get. Okay, so in that sense, these Bell states are maximally entangled and are very useful. Can we go to the next slide, please? Okay, so when we go to the mixed state, then things are a bit complicated. So suppose you have a mixed state for this density operator is rho AB. So you have a bipartite system consisting of two subsystems A and B. And then its measure will be just sum over I pi E, where E is some measure of entanglement of this rho ABI. But you will have to minimize to get the value for this measure. And this minimization process is often very complicated because this minimization is to be done over all decompositions of this density operator rho AB. So that is why for a mixed state, often it is very hard to compute any entanglement measure. But it was done for concurrence. It was done by Wouters, and he obtained this expression, which is max. Okay, so you order your eigenvalues of this operator given below this rho tilde, So again, if you see just if you look at pure state, so it is we have just gone to operator. That was a state. This is an operator. So you have to just take, just like there you take the complex conjugate. Here you take the complex conjugate. Then you have to apply this sigma to cross sigma. Then you will get for eigenvalues, and then then you take the square root of those. So you get rho tilde, then you get the eigenvalues of rho tilde, and then you take their square root, and then order them in the decreasing order. And then you just compute this lambda 1 minus lambda 2 minus lambda 3 minus lambda 4. And if a state is entangled, this will be positive. If it is not entangled, it can be either 0 or negative. So then your concurrence will be 0. So for a mixed state, we have a procedure, right? So you are given a density operator. You can calculate this rho tilde, which is the last expression. Then just calculate the eigenvalues of rho tilde. Then just take the square root and just use this formula. So concurrence is very useful when you're talking about at least 2-qubit system, whether it is a pure state or mixed. So this is one thing, so often, most famous entanglement monogamy relation is formulated in terms of concurrence, as we will see in a while. Can you please go to the next slide? Yeah. Okay. So another ingredient today is this Bell CHS inequality. I'm sure most of you know about it, but just to recap. So in this Bell CHS inequality, you have two parties, Alice and Bob. Both of them can measure two diachromatic observables, Alice A1, A2, and Bob B1, B2, with outcomes plus minus 1. Okay, so A1, A2, B1, B2, these are observables. Then you can take a specific combination of these observables, and which is ICHSH, after inventor of this CHS inequality, Clauser, Horn, Shimonoy, and Holt. Clauser got Nobel Prize, for actually trying to test this particular inequality. Okay, so if you have a theory which satisfies something what we call local realism, then this average will be less than or equal to 2. And if you calculate in quantum mechanics, then one finds that for lots of states, which especially when they are entangled, you can get value more than 2. Okay, so then quantum mechanics actually violates this inequality. So can we go to the next slide, please? Yeah. So okay, so just to see that how quantum mechanics violates this inequality. So we can choose some specific, specific A1, A2, and B1, B2. Remember, A1, A2 are observables measured by A, sometimes called Alice, and B1 and B2 are being measured by B, which we sometimes call Bob. So then you look at, now if you remember any pure 2-qubit state, I can write as lambda 0, 0, 0 plus lambda 1, 1 after Schmidt decomposition. So any 2-qubit pure state I can write in this one. Then I can calculate, this Bell inequality, which was basically average of ICHSH. In quantum mechanics, it means I take this expectation value. And if I calculate this expectation value, then it will be, as you see here, okay, 4 root 2 lambda 0 lambda 1. Now 2 lambda 0 lambda 1 is concurrence, as we saw a while ago. So this becomes 2 root 2 and multiplied by concurrence. Now, if you have a product state, then concurrence is 0, and then which is less than 2, right? So then the Bell inequality is not valid. Now, if you look at the Bell state, for which we saw concurrence was 1, then this value is 2 root 2. And actually, this is the highest value, which can be there in quantum mechanics. This is a kind of bound, Selson bound. Okay. So actually, but from here it may appear that for some entangled state, there may not be violation. For example, if C is less than 1 over root 2. But actually, there is a possibility of having another set of measurement settings. Then for those settings, we will see there is a violation. So there is a distance theorem which says that every pure entangled state violates CHSH, or sometimes we call Bell CHS inequality. Okay, so this is, as you see, for a pure state, it is a consequence of entanglement. If state is entangled, you have a violation. So that's why one might think it's just like you have entanglement monogamy, you may have Bell monogamy. So can we go to the next slide, please? Yeah, but things are actually not so simple if you go to a mixed state. So one of the famous two-qubit mixed state is known as this Werner state. I know, where you have this maximally entangled state phi plus, and there is this white noise there. Okay. So this is a mixed state, and this is a very interesting state, useful in a lot of contexts in quantum network. Often you have white noise, and which converts, your maximally entangled state into this kind of Werner state. So this state actually is entangled. So okay, so there is a criteria to find whether a state is entangled or not. There is you take partial transpose, see the eigenvalue of the operator. If it is negative, it isn't. So one can do that exercise, and one will find that the state is entangled when P is more than one third. But this state shows what we say phenomenon of hidden non-locality. Because so what it means is that there is some region, or there is some values of P for which the state is entangled, but there is no violation of Bell CHS inequality. Okay, and okay, so sometimes one may want to take help of some procedure, which may uncover this non-locality. Okay, so there exists a notion of something called filtering, where you apply some local operation on a mixed state, and sometimes if it is not showing violation of Bell inequality or Bell CHS inequality, after that local operation it starts showing. So that is, you can uncover this non-locality, and this is true for a number of mixed state, but not all. In particular, for Werner state, there does not exist any local operations which can uncover non-locality where state is entangled but doesn't violate Bell CHS. And actually, one can see easily that when P is more than 1 over root 2, it will violate Bell CHS. But between the region of 1 over root 2 and 1/3, where state is entangled, but there is no violation. Okay. But as we will see, we will encounter lots of states where by local operation you can uncover. This non-locality means you can have Bell violation. Okay, can we go to the next slide, please? Next slide, please. Yeah. So actually, so these are the two basic ingredients, okay, of whatever we are going to discuss in the rest of the talk. So in the case of multipartite system, the entanglement between different subsystem cannot take arbitrary values. Okay, so if A and B, so suppose you have a tripartite system ABC, entanglement of between A and B will limit how much entanglement B and C could have, or A and C could have. Okay, so one very canonical example here is that if you have a tripartite system, A and B are maximally entangled, but then C cannot be entangled with either A or B. As soon as you get entangle it with A or B, entangle between A and B will reduce. So there is a trade-off of entanglement between various subsystems. If you increase, entanglement between say A and B, suppose you take a state which has a higher entanglement between A and B, then you will have a correspondingly smaller entanglement between B and C. Okay, so there is a trade-off when it comes to entanglement. And this notion was formalized by Kaufman, Wouters, and Kundu using concurrence. What they showed, ki suppose you have a tripartite system ABC, so you look you look at subsystem AB. From that, you can find out the entanglement between A and B. Then you can look at subsystem AC, which will tell you what is the entanglement between A and C. Then you compare it with the entanglement of A with the rest of subsystem BC. Actually, here C is concurrence. So if you calculate C square, for subsystem AB and AC, and then A is BC, then this is a relation. And so this is sort of limits, as I was just saying, how much entanglement AB and AC could have, because there cannot be A and B cannot be have arbitrary entanglement, and AC cannot have arbitrary. Entanglement between A and C will be limited by whatever is there between A and B. So this is for tripartite, but one can generalize it for n-qubit systems also. Okay, so I should say there are certain measures of entanglement which have more than entanglement. They may not show these features, okay, but most of the measures, okay, they do show this monopole. Okay, so can you please go to the next slide? Yeah, so this was the monogamy for the entanglement. Okay, so as we just saw a while ago, as long as you have a pure state, whenever you have entanglement, there is a violation of Bell-CHS inequality. So this non-locality is very much associated with entanglement. Of course, when it comes to mixed state, then things are a bit more complicated. So one would expect also that there are limits to the sharing of Bell non-locality. So actually, so there are actually monogamy relations to quantify this limitation. So actually, there was a Bell monogamy relation which was introduced by Toner et al. So here you have a tripartite system ABC. So you look at the this we had this expectation value of this ICHS operator. So here I'm calling it BAB. Okay, so B is you see is below, which is actually nothing but Bell-CHS operator. So you calculate expectation value of this Bell operator or Bell-CHS operator, square it, and then you do same thing for subsystem AC. That value has to be less than or equal to 8. Here, just like earlier, A1, A2, B1, B2, they are dichometric observables. They take value -1 and 1. So this actually was generalized by Chin Fei and Lee Jost, and they showed that you can include another subsystem BC. Actually, there was a limitation in this first relation because they were making same set of measurements on A. So it was generalized where you could have all three subsystems A, B, AC, and BC, and you can make arbitrary measurements in the each case. Okay. When you are looking at BAB, you make arbitrary measurements on A and B's, which has no relationship when you make measurement for AC or BC. So here, so this value is less than or equal to 12. See, what is most interesting that you may want to see here is that if you remember, there was a limit of 2. It has to be more than 2 for Bell violation to occur. Now, suppose its value is 2. Then as you see, 2 square is 4, 4 into 3 is 12. So if its value is, for each subsystem, value is either 2 or less than 2, it is satisfied. Or in some cases, some subsystem can be entangled, but then other has to be, Okay, no, not entangled, I should say Bell violation. So suppose system BC shows Bell violation, then at least one of the subsystem AB or AC will not violate Bell. Because as you see, for, upper limit for locality is 2 and 4 into 3 is 12. So if any number exceeds 4 to violate Bell inequality, then at least one of the other number has to be less than 4. So then there will be no violation. So what is very interesting from here, you see that not all subsystem of any pure state which is tripartite will violate a Bell-CHS inequality. So, okay, so can you please go to the next slide?
So then in between, no, can I ask some questions, Bionando?
Oh, yeah,
Yes,
sure,
yes,
sure.
Yeah.
yes, carry on.
Yeah. See, Pankaj, it's actually very nice. So I have this, this one which you just now showed, that monogamy relation, that three-term monogamy relation, AB, AC, and BC.
Mhm. Mhm.
So, I mean, it is obviously asymmetric because A is occurring twice. Isn't that correct or no? No,
No,
A,
no, no,
B.
no, no. We are looking at subsystem AB, subsystem
Hmm,
AC, and subsystem BC, right?
BC.
So
Correct,
all
correct.
three subsystems. So there is no asymmetry.
Yeah, yeah,
AB is
yeah, yeah.
there,
Correct, correct, correct.
AC and BC, all three are there.
Hmm,
Actually, in the first monogamy, there is only two of them. It was because
right,
on subsystem for both Bell-Equally, they were making same interval.
right.
So if you want
So
to have more general expression, then you are making a so when you look at a subsystem AB, and then you will make arbitrary measurements on A and B, and you see the violation. Then go to subsystem AC, again arbitrary. So here measurement on A will not be impacted by whatever you measured when you were looking at subsystem AB.
mm-hmm,
Okay, so all three are, in that case, independent.
mm-hmm.
And what is most fascinating here is that one of the subsystems will not violate balance.
Okay.
This is somewhat very intriguing. Okay.
Mm,
So sorry, so maybe you can just share the slides again so I can
yeah,
sort of continue.
yeah, sure.
I can ask also a few questions in the
Ah,
meantime.
sure, sure. Sure, sure, sure.
So,
I'm sorry, just before that, so someone is trying to share my slides, right?
yes, I think we immediately see the presentation as and when they will share with us.
Sure, sure.
So,
Sure, sure, sure.
so
Sure,
in
sure.
the
Oh, okay.
meantime,
Sure, sure.
I think
So I can
so.
continue. So yes, please. Question?
Yeah. So if you introduce dissipation in your calculations, so will you see some interesting and useful results because you are excluding dissipation?
Yeah, actually, if I include dissipation, then it means my state will become a mixed state. And then we do have a similar monogamy relation, but things become just a bit more complicated because as I was telling you, in the case of some of the if you have a mixed state, then sometime it may not show, Bell violation. So analysis becomes more complicated, but this Bell monogamy relation still holds. So when you are including dissipation, it means you are including some noise. It means your state is turning to a mixed state, right? So there also you will have the same relation, Bell monogamy. I mean, whatever I have shown here. But analysis will become just a bit more complicated. Okay. So because our discussion is mostly here for pure state.
Yes, yes.
Just because to avoid complications coming from this.
Okay, I will continue then after the presentation.
Sure,
So I
sure.
think slides
Sure.
are visible. Okay, thanks.
Sure. Thank you. So I think we can go to the next slide. So this thing we have already discussed, these two monogamy relations. Right? So can we go to the next slide below it? Yeah, right. So here okay. So as you see, we have a AB, AC, and BC, right? So if you have a permutation symmetric state like GZ state or W state, then all subsystems will have same density operator. Rho AB, rho BC, Where you see all will be identical. If they are identical, then either so if if the AB won't violate Bell inequality, then same will be true of BC and AC because they are identical. If one will start violating, then all three will be violating there because they are identical, right? Because we have permutation symmetric state. So there are monogamy relations as I was saying, suggest that uh, just okay, so suggest that all subsystems cannot violate Bell inequality. And if this so happens, there is a violation of Bell monogamy. So as I was just mentioning, we have this special class, this permutation symmetric state, where all two-qubit subsystems have identical density operators. So since they are identical, so I would say if one violates, all violate. If one doesn't violate, none of them. Okay. So interesting thing there here it is the reason for looking at permutation symmetric state is that if I look at the and I can show okay there is a Bell violation after local operations, then all three will violate, and then Bell monogamy relation will be violated. Because as I just pointed out, for Bell monogamy relation to be satisfied, at least one of the subsystem will not violate. But if all three violate, it means the value is more than 2 for all of them. Then if I square that number, I will get more than 12. Okay. So one can look at like for example, most famous state which we have like GSZ and W state. And one can look at also more general symmetric state also, right? So I mean, let's see what happens about this Bell futures violation in this context. Can you please go to the next slide? Right. So let's start with simplest state 3-qubit GSZ state. Okay. As you can see, it is permutation symmetric. What it means is if you permute A and B or A and C or B, C, the state won't change. And if I take partial trace and I can get this rho 1 2, and as most of you know, for in the case of GSZ state, none of these subsystems are actually entangled. As you can see, rho 1 2 it is a mixture of product state. So it is not going to violate Bell's features inequality anyway. And since it is a mixture of product state, I cannot do anything because entanglement is zero and it is a product state, so it is not going to violate Bell features whatever I do to it. The same will be true about Rho 1 3 and Rho 2 3 because they are identical. So none of the subsystems violate Bell features. Okay, so it means Bell monogamy relation is satisfied for GHZ state. And if I can go to generalize GHZ in the sense that I can have a n-qubit GHZ state, and then because again those 2-qubit subsystem will not be entangled, so again Bell monogamy relation will be satisfied. Okay, I should mention though I wrote only for 3-qubit, one can generalize that Bell monogamy to more qubits. Okay, so for GHZ state is always satisfied. So now we can go to next famous 3-qubit state, which is W state. Yeah. So in this, if you look at this W state, it is basically you have 0 0 1, 0 1 0, and 1 0. This is my canonical W state. Now again all three subsystems will have same density operator, which I have written down here. And as most of you know, if I want to find out if there is entanglement, I take the partial transpose and then get the eigenvalues of the partially transposed density operator. And then here I have written down these eigenvalues, and as you can see, one of the eigenvalues is negative. So this state is entangled. The point being then if you take a 3-qubit W, all three of its subsystems are entangled. Okay. So now let's go to which is unlike GHZ. As you saw for GHZ, all three subsystems are not entangled, but here they are. Can you go down, please? Can you go to the next slide? Okay, so I mean, just like there is a criteria. See, good thing about two-qubit state is we know we have a criteria by Hodecki family to find whether it is entangled or whether it violates the SUHS system. So sorry, but for entanglement we have this Paris-Hodecki criteria which showed the partial transpose criteria, and for this for Bell violation there is also well-defined criteria that you suppose given a row you calculate what is known as this T matrix, which is in some sense correlation matrix, which is you just row 1 2 you multiply by sigma I plus sigma j, take trace, it will give you this matrix. Now using this matrix you can compute the another matrix U, which is T dagger T. Now then you can calculate the eigenvalues of this matrix U. If sum of the two largest value is 1 or more than 1, then it violates Bell CHS. And in this case, obviously two largest sum up to 8 by 9, which is less than 1. So what you see this row 1 2 does not violate Bell CHS. Same thing is true about row 1 3 and row 2 3 because they are same. So what we are finding here, if you look at 3-qubit W state, all subsystems are entangled, but none of them violate Bell CHS. Okay. So can you please go to the next slide? Okay, so this is where this whole idea of applying local operation comes. So so now I have this 3-qubit W. I can calculate row 1 2, and I can check and see that row 1 2 is actually a mixture of a Bell state and 0 0. Now actually this was shown long ago by Jisha and Popescu that there if you apply some local operation, which is called sometimes filtering operation, then you can see the Bell violation in some cases, which you didn't see before applying this local operation. So here, if we chose to apply a particular operation, which you see F here, where epsilon is some number which will determine the strength of this filtering operation, then we calculate what is the density operator after this filtering operation. Okay. So here you can see, we have this, this new density operator after this local operation. Can you please go down? Can you go to the next slide? Yeah, so again I can calculate this matrix U for it, and there you can clearly see if so if I take the two largest eigenvalue, which are first two, if I add them and then I require them to be more than 1, then I find a condition on this filtering strength epsilon. So as long as this filtering strength is if that epsilon is less than some particular value which you see here, there will not be Bell violation. But if I choose epsilon to be less than that, this square root of 2 into root 2 minus 1, then you will see Bell violation. So what we are seeing here, and again remember row 1 2, row 2 3, and row 1 3, they are identical. So what we are seeing here, local operations which cannot increase entanglement, will lead to the Bell violation for all three subsystems. Okay, so by this local operation, what you see, we all are violating. So Bell monogamy, which required that at least one of the subsystems will not violate inequality, but here all three are violating. So total will increase. Total will be more than 12, and so it will violate Bell monogamy. Okay. So now we can go to the next slide. So this is about 3-qubit. Now we can generalize it to n-qubit. So let's look when I say, so we can have a in some sense sometimes we can call it generalized W or just W. So this for n-qubit where one of the entry for each term is 1. Okay. Then I can trace out n minus 2 of the qubits. And then I will again get a row 1, 2. And again, one can see that this state is entangled. Okay. Can you please go to the next slide? There one can see that. Please go to the next slide. Yeah, right here. So here are the eigenvalue for partial transpose, and this is one specific eigenvalue because when n minus 2 is square, because n is more than 2, and then our square root will be more than n minus 2, and when we negative sign, it will be negative. So state is entangled. Okay. Now I can see what is my U matrix, which I discussed earlier. Now, if I look at some of the two largest eigenvalues, like when n is more than 3, because 4 over n square over 4 over 8 over n square, or sometime when is more than 6, last one will also be part of it. But in none of those cases, as long as n is equal to and more than 3, sum will be less than. So again, same thing is true. I start with 1 qubit W state. I look at a 2 qubit subsystem. None of them will violate Bell inequality. So again, corresponding Bell monogamy will be satisfied. Can we please go to the next slide? But again, I do the same exercise. I use a particular filtering operation. And again, I calculate matrix U. And can you please go to the next slide? Yeah, so in this case, I will get two eigenvalues. And what I find that as long as this parameter h is less than some value, some of the two eigenvalues will be more than one. Okay. So here is some algebra here, basically, which tells you what is the condition. Because I want some of the two largest eigenvalues to be more than one. So I do some of this algebra, then what I find, as long as h is less than this particular value, some of the two largest eigenvalues more than one, and there is a value. So again, what we see if you will enter it, again there is a Bell violation which leads to the violation of the Bell monogamy. So as long as we are looking at 2 qubit subsystems, I can do analytical calculations and I can see it easily. But one can go beyond Bell CHS. As you see, we are talking multi-partite state. You can look at 3 qubit subsystems, 4 qubit subsystems, and all. So for that, we need to generalize the Bell monogamy, which I mentioned earlier. Can you please go to the next slide? Right. So now suppose I have 4 qubit subsystem. Right. So then I look at 3 qubit subsystems. So really 4 of them. Then I can introduce in analogy with our earlier, Bell monogamy, a Bell monogamy for 3 qubit subsystem. Okay. So if you remember, there's somewhere, right hand side of the monogamy where the sum of the largest possible local value, which was 2. So 2 square plus 2 square plus 2 square was 12. So something similar one can have here. So for each Bell inequality, you will have some maximum local value. You just square them and add them, and that will be this quantity called CQ. Now, when we go to beyond bipartite, there are many Bell inequalities. I mean, there is n number of them, right? For each of them, this C3 will be different. So some of the well-known inequalities are, there is a Mermin inequality, there is a Sutcliffe inequality, there is also what we call minimum scenario facet inequality, and there is one inequality in one of our earlier papers. So what we are doing, we are looking at all those 4 Bell inequalities. Can you please go to the next slide? Right. So here I have written down these 4. You can call them, Bell inequality. One of them is called Mermin. So what we have here, we have 3 subsystems, and we are making 2 measurements each on all of these subsystems. A1, A2, B1, B2, C1, C2. They are dichromatic and take value plus minus 1. This is true for Mermin and Sutcliffe. But in the case of minimal scenario from one of our papers, we make only one measurement in one of the on one of the qubits. Okay. So like for in last one, as you can see, our system we are making only one measurement. Okay. So what we are doing now, then analyzing this Bell monogamy for all of these four different inequalities. Okay. And all of them are known to be violated in quantum mechanics. Okay. And at least for wide varieties of states. Okay. Can you please go to the next slide? Right. So here, so let's look at again now 4-qubit W state. I can find 3-qubit subsystem density operator. Then I can find the maximum value in quantum mechanics. By calculating the expectation values of those operators. And then what I find is minimum values, what I'm getting for min-2, saturation 2.83, minimum scenario 2, and one of our paper 1.4. So sorry, I mean there was some phone call. Sorry. So okay, so if you remember, for Mermin highest local value is 2, for search with me 4, for minimal scenario 2, and for our matrix it was also 2. Okay, so what you see is Bell, I mean there is no violation of any of those four Bell inequalities. Can you please go to the next slide? I think we started a bit late. Okay. Okay, so now here we see if I apply a specific filtering operation, then depending on value of h, you see the violation. So you see here, Mermin local value was 2, and when you take h to be as large as 0.99, it is becoming more than 2. But for listening to be more than 4, you have to choose h around 0.37 or lower. For minimal scenario also you have to get value, I mean it can be any value smaller than 0.37, even a bit larger, because we don't have a boundary. Okay? Or in the case of this from our paper, it can be 0.55 or less. So again, what we see after filtering, all these 3-qubit Bell inequalities, all of them are violated. So it means our new this Bell monogamy relation, which was one of the slides before, will again be violated. Okay. So can you please go to the next slide? Yeah. So actually, so here this is we look at even more general situation where you have n qubit generalized W, but you look at n qubit subsystem, okay, which is n qubit subsystem. So if you have a n is say 3, then actually this plot shows you, what is the value of h, below which you will have the Bell valuation. And as you see, as the number of qubit increases, which is this n, so you will see that you will need a smaller and smaller value of this filtering. But the point being, for you will have the violation for 3-qubit Bell inequality, and then this 3-qubit monogamy relation, for any of the n qubit Bell. Can we go to the next slide? Right, actually, one can look at 5-qubit generalized W, and then we have to introduce this 4-qubit. Suppose I look at 4-qubit Bell inequality. Here I have written down 2 of them. One is we call minimal scenario, other is from one of our papers. And again, one can show the Bell monogamy is respected before filtering, because they don't violate Bell inequality, those subsystems. But if I choose value of h as written here, less than 0.59 for the first inequality and 0.91 for the second inequality, again there is a Bell violation, and this leads to the violation of Bell violation. Can you please go to the next slide? Yeah, so this I have just given some result here, that is you can go to any subsystem. So you start with n qubit, then you look at any n qubit subsystem, then you can always find the h. Okay, so to start with any of the subsystem, so you have n qubit to start with, you look at n qubit, none of them will violate m partite Bell. You look at some m partite. But once I apply this filtering operation for this H, which is less than on the right hand side, you will see that. Okay, and it means violation of monogamy. Can you go, so now coming to the end basically, can you please go to the next slide? Okay, so what we discussed here until now was permutation symmetric state. But one can look at a state which is not permutation state. So as most of you know, for a 3-qubit state, this is a general parameterization which was given by Asian and collaborators. So it has this 5 parameters, but 6 parameters, 5 are independent. And but one has to choose some values of these parameters to do any analysis. Okay. So we chose some specific values like 50, lambda 0, 0.1, lambda 10, lambda 2, 0.2, lambda 3, 0.3. We chose values such that all subsystems were entangled. Okay, because only then there is a possibility of Bell violation, right? So again, we found that none of the subsystems, row 1, 2, only one of them violates actually Bell CHS, row 2, 3, row 1, 3, and row 1, 2 don't violate. So again, monogamy is respected. But again, by filtering, I can see row 1, 2, and row 3 also violate Bell CHS. And again, you have a violation of monogamy. So this is true for any pure state, but this one can generalize it to any mixed state. So now let me come to the conclusion. Okay, so whole point of this talk has been that like entanglement, there is a limit to sharing of non-locality in the case of multiparticles. And this limit of sharing leads to the monogamy relation. Okay. So for considering this permutation symmetric states, we saw 2-qubit subsystems of those permutation symmetric states don't violate the CHS and monogamy is respected. But by local filtering, you can see that Bell CHS is violated and then monogamy is violated. This is showed for W, but actually one can look at more permutation symmetry, where it turns out in some cases, you won't see the violation of monogamy because filtering doesn't work in the case of some states. Okay, so we also went beyond, say a 3-qubit subsystem. We also looked at multipartite Bell inequalities. Even there we found the corresponding monogamy relations are respected before local operation, but not after local operation. Okay, and we also showed same thing for a node generation. Okay, so I think the basic thing here is this monogamy tells you some of the such system must not violate Bell for it to be monogamy to be respected. But what we have shown is by local operation, you can have the violation of Bell inequality. So there's monogamy. So you do need a more robust monogamy. Okay, I think I'm ending here. So thank you.
Thank you, Professor Agrawal. Now we may have 2 quick questions. If you have some questions.
I have one question. So
Sure.
thank you for a very interesting and informative talk. So you have considered in your talk, you have considered discrete variables relations. So my question is, can we apply them for continuous variables? In that case, maybe some adaptations are required, and then question comes, what kind of adaptations we may require?
Right. Actually, thing is, even whatever I discussed was not only for discrete case, but also only for qubit.
Okay, so those are valid also for continuous variables. No adaptations are required. Okay. Thank you.